Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is series parallel circuit analysis. Our objective today is to take a close look at series parallel electrical relationships, circuits that combine the characteristics of both basic series and basic parallel circuits, and discuss basic properties for series parallel configurations. We'll make use of previously discussed series and parallel properties to determine unknown properties based off limited observations. Additionally, we'll discuss how voltage, current, and power is proportionally distributed within a series parallel circuit, as well as the effects of short circuits and open circuits inside series parallel circuits. Let us begin this lecture with a review of basic series and basic parallel properties. Let's start with some universally acceptable analysis techniques, notably Ohm's law and the power equations. Regardless of the flavor of the circuit you're performing an analysis on, you should be able to whip out any permutation of Ohm's law or the power equations to arrive at any answer you seek. Notably, current is equal to voltage divided by resistance, voltage is equal to current times resistance, and resistance is equal to voltage divided by current. Power dissipated by any element is equal to the voltage across it times the current through it squared times its resistance, or the voltage across it squared divided by its resistance. Additionally, we can always make use of the simple and powerful statement that power input to a system is always equal to power output. Regardless if the circuit is a series parallel, or some crazy complex circuit you've never seen before, all these basic properties should always hold true. Ohm's law, the power equations, and power in always equals power out. Now let's paint a line down the center of the screen and put all the purely series properties on one side and all the purely parallel properties on the other. Current through elements in series is the same. Voltage across elements in parallel is the same. Kirchhoff's voltage law is an especially useful circuit analysis technique for series circuits. The sum of voltage rises should equal the sum of voltage drops. What goes up must come down. Kirchhoff's current law is an especially useful circuit analysis technique for parallel circuits. The sum of currents entering a node should equal the sum of currents leaving a node. What goes in must come out. Series circuit analysis employs a handy shortcut called the voltage divider rule. Parallel circuit analysis employs a handy shortcut called the current divider rule. The largest resistor in a series relationship has the largest voltage drop and dissipates the most power. The smallest resistor in a parallel relationship has the largest current through it and dissipates the most power. The smallest resistor in a series relationship has the smallest voltage drop across it and dissipates the least amount of power. The largest resistor in a parallel relationship has the smallest current through it and dissipates the least amount of power. Equal resistors in series relationships have equal voltage drops and dissipate equal amounts of power. Equal resistors in a parallel relationship have equal current draw and dissipate equal amounts of power. Adding resistors in a series relationship decreases source current draw because the total resistance increases via the series summation of resistances formula. Adding resistors in a parallel relationship increases source current draw because total resistance decreases via your choice of the several parallel resistance formulas. A shorted element in a series relationship will remove that element from consideration. No current will flow through it and no voltage will be dropped across it. An open element in a parallel relationship will remove that element from consideration. No current will flow through it and no voltage will be dropped across it. An open inside a series relationship will cause all current through the series circuit to cease. A short inside a parallel relationship will cause current to dramatically and potentially catastrophically increase. This comparison between the two basic electrical relationships, series and parallel, is now complete, and I'm going to take the unusual step of reaching out of the internet and grabbing you by the collar with both hands and shaking the living daylights out of you. Pay attention because I am about to blow your mind. I have nothing left to teach you about circuit analysis. The rest is just party tricks. These series versus parallel properties are always true, and their application to circuit analysis and troubleshooting must become real, visceral, and instinctual. This cannot be accomplished by watching an online lecture or playing around with circuit simulation software. You must get inside a hardware lab and practice and apply these techniques on real-world components using real-world instrumentation. You will make mistakes and things will not go smoothly at first. But realize elements in series with one another must necessarily carry the same current through them, and elements in parallel with one another must necessarily have the same voltage across them. The sum of voltage rises always equals the sum of voltage drops. What goes up must come down. The sum of currents entering a node must equal the sum of currents leaving a node. What goes in must come out. Any iteration of Ohm's law or the power equations is always true, as is the incredibly simple and useful observation that power in always equals power out. Here's the especially crazy part. These facts are true for all circuits, including those not purely in series nor purely in parallel. All basic circuit analysis techniques can be boiled down to these simple observations, and the only essential point I can add to this checklist is a bit of personal advice. Visualize circuits from the perspective of flowing current, and think about voltage at the nodal level. If current has no choice but to flow through a single path, elements in that path are in series with one another. If current has a choice between paths, those paths are in parallel with one another. If two paths are hooked to the same two nodes, these paths must necessarily have the same voltage across them. Notice the slight twist in phrasing I'm employing, saying path instead of element or resistor or component, implying these properties of purely DC series and purely parallel circuits can be extrapolated into larger and more complex circuits, including DC series parallel circuits, AC series circuits, AC parallel circuits, AC series parallel circuits, and more. There are hucksters and textbooks of ill repute that try to sell you special series parallel analysis skills dressed up in fancy names like reduce and return, assumed value backtrack, and ladder networks. But these are unnecessary to the point of being considered fraudulent. Never, ever reduce and return. It won't work if your circuit contains unknown values. Why backtrack when your goal is forward progress? Don't learn special purpose skills of limited value. Use what you already know and simply and directly solve for the desired unknown quantities you seek. These techniques work every single time, and they're techniques you already know and have plenty of experience with. Consider the simple utility of these basic series and basic parallel circuit properties when combined with the two-step process of visualizing the circuit from the perspective of flowing current and thinking about voltage at the nodal level. I'll start by assigning some nodes, A, B, and C. In this series parallel circuit, flowing source current, IS, enters node A and has a choice, either to travel through R1 or R2, splitting into two branches I'll call I1 and I2. The branch currents I1 and I2 recombine at node B. R1 and R2 are clearly in parallel with one another. Current leaving node B has no choice but to travel through R3 to get to node C. It can be said that R3 is not in series with R1, nor R2 singly, but rather R3 is in series with a parallel combination of R1 and R2, something I'll call R prime. Any further reduction of this circuit beyond this level of simplification is absolutely unnecessary. We have reduced this formerly series parallel circuit to a simple series circuit and can apply basic series properties. How would current through R prime compare to that of the current through R3? The current through elements hooked in series is the same. Additionally, time-saving shortcuts like the voltage divider rule can be applied to this simple series circuit, as well as old standbys like Ohm's law. Stepping back up to our original configuration, using our previous understanding of Kirchhoff's current law, what goes in must come out. It can be said that the source current IS proportionally splits into I1 and I2, no more, no less, since there are no other additions nor subtractions to this path. IS equals I1 plus I2. Additionally, if I1 and I2 recombine at node B, this means that I1 plus I2 equals I3, the current through R3. Finally, if I3 travels into the negative terminal of our source, it must come out of the positive terminal of our source. It can be therefore stated that I3 is equal to our source current Is. Our Kirchhoff's current law analysis of this circuit suggests Is equals I1 plus I2, which equals I3. Consider voltage distribution within this same circuit at the nodal level. Using Kirchhoff's voltage law, we can examine the voltage distribution of this series parallel circuit. Start here. Travel in this direction. There is a voltage rise of E. There is a voltage drop of VAB. There is a voltage drop of VBC. Substituting in the voltage rises or drops across the components hooked between these double subscript voltages described by this loop, we are left with E equals V1 plus V3. Other loops exist. Start here. Travel in this direction. There is a voltage rise of E. There is a voltage drop of VAB. There is a voltage drop of VBC. Substituting in the voltage rises or drops across the components hooked between these double subscript voltages described by this loop, we are left with E equals V2 plus V3. Yet another loop exists. Start here. Travel in this direction. There is a rise of VAB. There is a drop of VAB. Substituting in the voltage rises or drops across these components hooked between these double subscript voltages described by this loop, we are left with V1 equals V2. This KVL analysis suggests that V1, the voltage drop across R1, is equal to V2, the voltage drop across R2. This is supported in our earlier pure series circuit simplification, where R1 in parallel to R2 between nodes A and B is exchanged for R prime. It makes sense. The voltage across paths in parallel is the same. V1 equals V2 equals VR prime. With this understanding, I could perform an additional iteration of KVL on our simplified series circuit as E equals VR prime plus V3. Notice at no time did I introduce any new conceptual understanding to the analysis of this seemingly advanced series parallel circuit, but rather used basic properties of series and basic parallel circuits. Notably, current in series paths is the same. Voltage across elements hooked in parallel is the same, and our understanding of KVL in that what goes up must necessarily come down. I must reiterate, I have not introduced any esoteric weirdness, legal mumbo-jumbo, nor double secret black magic. All these properties kind of make sense if you visualize circuits at the nodal level and from the perspective of flowing current. Finally, and this is important, at no time was it absolutely necessary for me to reduce this to a single resistor, RT, the total resistance seen by the source, and then painstakingly backtrack, reapply, and return to my original configuration to make use of basic pure series and pure parallel properties. Although this could have been done if you're unusually hard-headed. Current through R prime should equal current through R3, and VR prime plus V3 should equal our total applied voltage. Any further simplification of series parallel circuits beyond a purely series circuit or a purely parallel circuit is like taking your car apart to find a quarter under the seat. Just look under the seat. The only element lacking in this circuit is component values. If you feel confident, by all means, pause the lecture and take a shot at this. E is an 18-volt source. R1 is an 80 ohm resistor. R2 is a 120 ohm resistor. R3 is a 32 ohm resistor. I'm asking you to solve for the voltage drop across each component and the current through each component as well as source current. You are flatly prohibited from solving for total resistance until the very last step. Do not reduce in return. This is a waste of your time. Use the simple and direct method I showed you to arrive at the correct results by applying basic series and basic parallel properties. You may have used different methods in a different order, but ultimately our answer should agree. R1 in parallel with R2 is simplified as a 48 ohm resistance, R prime. This two resistor pure series circuit is our desired level of simplification, and any further reduction is a waste of time. My go-to technique for pure series circuit analysis is the VDR. The VDR is set up to solve for VR prime, the voltage drop across our imaginary resistor R prime, and coincidentally, The voltage drop across both R1 and R2, since they're in parallel, is as follows. Substituting in the necessary values, we find VR prime to be 10.8 volts. Therefore, V1 equals 10.8 volts and V2 equals 10.8 volts. We can use another iteration of the VDR or Ohm's law to solve for V3. However, we can also use Kirchhoff's voltage law to solve for V3. Our earlier KVL analysis suggests E equals VR prime plus V3. Substituting in the given value of our source and the calculated value of VR prime, and solving for V3, we find V3 to be 7.2 volts. All unknown voltages have been solved for, and we can use Ohm's law to solve for the current through these resistors. Let's solve for I3 first. I3 equals V3 divided by R3. Substituting in the necessary values, we find I3 to be 225 milliamperes. Therefore, IS also equals 225 milliamperes. Given we know voltage across both R1 and R2 to be 10.8 volts, we could use Ohm's law to solve for the current through either one of them, or both. However, since we're well versed in the current divider rule, let's apply it to solve for current through one of these resistors. My choice is I1. The CDR set up to solve for I1 is as follows, or this alternate configuration. Substituting in the necessary values, either configuration of the CDR finds I1 equals 135 milliamperes. We could again apply CDR to solve for I2. However, we could also make use of our previous understanding of KCL, where I3 equals IS equals I1 plus I2. We can substitute in our previously calculated value of the source current and our freshly calculated value of I1 to solve for I2, where I2 equals 90 milliamperes. All desired voltage and current values have been solved for, and at no time was it absolutely necessary to solve for total resistance, reduce and return, assume a value and backtrack, or perform a complicated ladder network analysis. All circuit properties are immediately accessible via skills you should already feel comfortable applying with little outside guidance. Ohm's law, the power equations, current through elements in the same path is the same, voltage across paths in parallel is the same, what goes up must come down, what goes in must come out. This being said, total resistance calculations are a great means of checking one's work. After all has been said and done, the total resistance seen by the source should be equal to the source voltage divided by the source current via Ohm's law. RT equals E divided by IS. The total resistance calculated in this manner should be equal to the total resistance calculated via traditional resistance methods. In this case, one would combine R1 in parallel with R2 to make an imaginary resistor R'. This imaginary resistor R' is then summated in series with R3 to solve for total resistance RT. It can be said that total resistance seen by the source equals R1 in parallel with R2 in series with R3. Notice the parentheses. This is to imply that R1 must be taken in parallel with R2 first, then this parallel combination is added to R3. In this case, both methods yield a total resistance of 80 ohms. I'm reasonably confident our answers are correct, and we can move on to the next illustrated example problem. By the way, if you're hoping for something new and earth-shattering in this lecture, you came to the wrong place. I will apply no new techniques and make no dramatic conceptual leaps. I probably won't even make new jokes. One learns series parallel circuit analysis by performing series parallel circuit analysis. By all means, pause the lecture and see if you can solve for the quantities of interest. For this particular series parallel circuit, R1 is 250 ohms, R2 is 750 ohms, R3 is 500 ohms, E is 20 volts. Solve for the voltage drop across each component and the current through each component as well as source current. You're expressly forbidden from reducing the circuit to a single total resistance and returning to solve for unknowns. You don't need to do this and it will only waste time. Solve for voltage and current directly using basic series and basic parallel properties. You may have used different steps in a different order, but ultimately our answers should agree. First, before you enter a single number into your calculator, what is the relationship of IS, I1, I2, and I3 And what is the relationship of E, V1, V2, and V3? Meaning, are any of these values equivalent to one another, or do any of these values summate to other values? The point is, don't make yourself solve for things you don't have to. Current in a single path is the same. Voltage across paths in parallel is the same. For every rise there is a drop, and what goes in must come out. The first step in series parallel circuit analysis is to visualize this circuit at the nodal level and from the perspective of flowing current. I'll start by assigning some nodes, A, B, and C. In this circuit, source current enters node A and has a choice to travel through two paths. These two paths are clearly in parallel with one another. One of the paths is just R3. However, the left path has R1 and R2 clearly in series with one another. Once current leaves node A and travels through the left branch, it has no choice but to travel through R1 and then R2. It can be stated that I1 equals I2. Since source current is splitting as it enters node A, it can be said that source current is equal to the summation of I1 plus I3, or I2 plus I3, since I1 equals I2. Additionally, since we're aware that R1 and R2 are in series with one another, we can think of the left-hand branch being a single imaginary resistor, I'll call R prime, being the summation of R1 and R2, strung between nodes A and C. In this simplification, node B is no longer accessible. However, using our two-resistor simplification, we're clearly left with a purely parallel circuit, where the voltage drop across R prime is equal to that of R3. And because the source voltage is applied across to node A and C, it can be stated that E equals VR prime equals V3. Given R prime is the summation of R1 and R2, it can also be stated that VR prime equals V1 plus V2, which equals V3, which equals E. If R prime is in actuality R1 in series with R2, it would stand to conjecture that those resistors that compose R prime should drop representative portions of VR prime. If we now crack open R prime to be the series combination of R1 and R2 and apply Kirchhoff's voltage law, we realize this loop contains a rise of E and a fall of V1 plus a fall of V2, where again V1 plus V2 should equal V3. Notice my first steps had nothing to do with numerical calculations, nor did I have to resort to solving for total resistance. I applied Kirchhoff's current law and Kirchhoff's voltage law. Long story short, I didn't just bebop into an ambush. I planned out a course of action, and all I've got to do now is execute it violently. E equals VR prime equals V3. KVL suggests that V3, the voltage drop across R3, is 20 volts. This makes sense. R3 is in a perfect parallel relationship with our source and the imaginary resistor R prime. Voltage across paths in parallel is the same. E equals V1 plus V2 equals V3. If we crack open R prime, the series combination of R1 and R2, this also suggests that V1 and V2 drop representative portions of this same 20 volts. I'll use the VDR to solve for V1. Notice the VDR set up to solve for V1 includes only those elements in series with one another for that path. In this case, only R1 and R2. R3 is not in this path and is in no way influencing the voltage drop experienced by these two resistors. Substituting in the necessary values, we find V1 to be 5 volts. We could again use the VDR or various permutations of Ohm's law to solve for the remaining voltage drop V2. However, we can also make use of our earlier statement of KVL that E equals V1 plus V2. Substituting in the necessary values and solving for V2, we find V2 to be equal to 15 volts. Given we solve for all unknown voltages, we can now solve for unknown currents using Ohm's law and wise application of Kirchhoff's current law. Let's start with I3. I3 equals V3 divided by R3. Substituting in the necessary values, we find I3 to be 40 milliamperes. Given our earlier understanding that I1 is equal to I2, it is only necessary to solve for one and not the other. I1 equals V1 divided by R1. Substituting in the necessary values, we find I1 to be 20 milliamperes. Since R2 is directly in series with R1, it can also be said that I2 is also 20 milliamperes. Finally, source current is summation of both branches of our perfect parallel circuit, being that current bound for R' and R3. Current traveling in the right-hand branch is I3 at 40 milliamperes. Current in the left-hand branch is 20 milliamperes. Therefore, source current is 20 plus 40, or 60 milliamperes. All desired unknown quantities have been solved for simply and directly using basic series and basic parallel properties, and at no point did I ever reduce and return, dilly-dally, dither, or delay immediate satisfaction. Opportunities to check my work exist, and if you have time, it is always a recommended practice to do so. First, VR', the voltage across the imaginary resistor R', comprising the series combination of R1 and R2, should be the summation of V1 and V2. 5 plus 15 does in fact equal 20. Good here. Second, does Ohm's law support our earlier assertion made using KCL that I1 equals I2? Having already solved for I1 using Ohm's law, a second permutation of Ohm's law from the perspective of R2 suggests that I2 equals V2 divided by R2. Substituting in the necessary values, we find I2 does in fact equal 20 milliamperes as expected. The same current travels through it as does R1 because it's in the same path with R1, and there are no additions nor subtractions to this single path. Finally, one can use source current to solve for total resistance via Ohm's law, where RT equals E divided by IS. Substituting in the necessary values, we find that the 20-volt source is behaving as if it was supplying 60 milliamperes to a 333.3 ohm resistor. This simple Ohm's law analysis supports a painstaking reduction of this series parallel circuit into a single resistor. R1 and R2 in series is a 1 kilo ohm resistor. A 1 kilo ohm resistor in parallel with a 500 ohm resistor also presents a total resistance of 333.3 ohms. All our values check out, and I'm reasonably confident we can move on to the next illustrated example problem. If you're getting the sneaking suspicion that I don't like the reduce and return technique commonly presented in basic electronics textbooks, you're right. Reduce and return not only waste your time, it's absolutely useless in circuit analysis scenarios incorporating unknown values like our next illustrated example problem. Only your thorough knowledge of basic series and basic parallel properties can guide you to the correct solution for such situations lacking complete information. Here we're presented with a series parallel circuit in which the source is known to be 24 volts, and we're observing a 14.4 volt drop across the unknown resistor R3. R1 and R2 are known to be respectively 500 ohms and 2 kilo ohms. Pause the lecture and take your best shot at solving for the desired unknowns. We're being asked to solve for source current through each element, the voltage drops across R1 and R2, and the value of the unknown resistor R3. Use basic series and basic parallel circuit properties only. Since this circuit incorporates unknown resistors, you cannot rely on the reduce and return technique. Don't even attempt to reduce it to a single total resistance because you can't. Visualize this circuit at the nodal level and from the perspective of flowing current. Current in a single path is the same. Voltage across paths in parallel is the same. For every rise there is a drop, and what goes in must come out. I'll start by assigning some nodes, A, B, and C. Source current leaves the positive terminal of our source and must pass through R1. It can be said that IS equals I1. When it gets to node B, it has a choice to travel through R2 or R3. It can be said that IS equals I1 equals I2 plus I3. R2 and R3 are clearly in parallel with one another. The voltage drop across paths in parallel should be the same. R2 and R3 are between the same two nodes B and C, and given voltage as a 2-point measurement, should experience the same voltage drop. V2 equals V3. If we combine R2 and R3 in parallel into an imaginary resistor I'll call R', it is readily apparent via KVL. The voltage rise E is equal to the voltage drop V1 plus the voltage drop VR'. Since R' is the parallel combination of R2 and R3, it can be said that V2 equals V3 equals VR'. Therefore, the 14.4 volt drop experienced by the unknown resistor R3 should also be experienced by R2, the 2 kilo ohm resistor. V2 equals 14.4 volts. And via Ohm's law, I2 equals V2 divided by R2. Substituting in the necessary values, we find I2 equals 7.2 milliamperes. We've kind of run out of handholds regarding the parallel combination of R2 and R3. We know V2, R2, and I2, and we know V3. However, we don't know R3, I3, or the current entering or leaving this parallel combination. Or do we? Our earlier KVL analysis suggested that E equals V1 plus VR prime. Given VR prime equals V2, which equals V3, we can substitute in the given source and V3 value and solve for V1, where V1 equals 9.6 volts. Via Ohm's law, I1 equals V1 divided by R1. Substituting in the necessary values, we find I1 equals 19.2 milliamperes. Given our earlier KCL analysis suggests IS equals I1, we are also aware that IS equals 19.2 milliamperes. Additionally, our earlier KCL analysis suggests IS equals I2 plus I3. Substituting in the calculated values of IS and I2 and solving for I3, we find I3 to be 12 milliamperes. Via Ohm's law, R3 equals V3 divided by I3. Substituting in the necessary values, we find R3 is a 1.2 kilo ohm resistor. All unknown quantities have been solved for using basic series and basic parallel properties only in a systematic and recognizable fashion. Visualize series parallel circuits at the nodal level and from the perspective of flowing current. Current in a single path is the same. Voltage across paths in parallel is the same. For every rise there is a drop, and what goes in must come out. Before we move on to the next illustrated example problem, let's consider the effects of shorts and opens inside series parallel circuits. It may help us to again refresh the differences between basic series circuits and basic parallel circuits when encountering these two errors. A shorted element in a series relationship will remove the shorted element only from consideration. No current will flow through the shorted element and no voltage will be dropped across the shorted element. This being said, since the shorted element has been removed from consideration and no longer presents opposition to the source, and current through the series circuit will increase. With increased current draw, the remaining series element will have larger voltage drops. An open inside a series relationship will cause all current through the series circuit to cease. Since no current is flowing through any element, no element will experience a voltage drop. All voltage will be dropped across the open. An open element in a parallel relationship will remove that open element only from consideration. No current will flow through it, and no voltage will be dropped across it. This being said, since the open element has been removed from consideration, it no longer provides an additional path for current, and the source experiences an increase in opposition, and source current will decrease. A short inside a parallel relationship effectively removes the parallel combination's opposition. With no opposition, source current will dramatically and potentially catastrophically increase. Pertaining to the resolution of shorts and opens inside series parallel circuits, my only guidance is this. It depends. It depends upon the series parallel circuit, and it depends on where the short or where the open occurs within that particular circuit. This is to suggest that series parallel circuit analysis and troubleshooting isn't prefabricated drone work anymore, and you've got to really get down and dirty and think about it. Visualize the circuit at the nodal level and from the perspective of flowing current. Current in a single path is the same. Voltage across paths in parallel is the same. For every rise there is a drop, and what goes in must come out. Consider an open at node B, necessitating the introduction of another node I'll call B', effectively separating R1 from the parallel combination of R2 and R3. In our simplified pure series circuit, there is an open between R1 and R'. No current will flow through the entire circuit since there is no closed path. Since there is no current flowing through any element, no element will experience a voltage drop. All voltage will be dropped across the open, B to B'. Alternatively, consider another open, also at node B. However, this time R2 only falls loose because of an off by one or errant connection. This necessitates the introduction of another node I'll call B double prime at the top of R2. In this case, there is still return path for current via R3. However, this circuit will behave radically different than previously. In this case, R1 and R3 present series opposition to the source rather than R1 in series with a parallel combination of R2 and R3. R3 by itself will present more opposition in contrast to the parallel combination of R2 and R3. Long story short, source current will decrease because opposition increased. Both R1 and R3, since they are now in series with one another, will experience the same current of 14.1 milliamperes. And the voltage drop across R1 will be roughly 7.1 volts, and the voltage drop across R3 roughly 16.9 volts. The summation of voltage drops still equals the voltage rise. However, this is not the series parallel circuit you intended to build, and only by having done the calculations prior to making observations would you be aware of this. Do the calculations first. Don't walk into a gunfight carrying a dull knife. Now consider a short across R3. This short effectively removes the entire parallel combination of R2 and R3 from consideration. In our simplified series circuit representation, this would be akin to shorting out R'. R1 is the only opposition in this circuit. Opposition has radically decreased, and current will increase to 48 milliamperes. R1 will experience the entire voltage drop of 24 volts. The voltage drop across the parallel combination of R2 and R3 will be 0 volts, since all current is being diverted through the short. I must reiterate, the only way you can detect a malfunction or troubleshoot an error is if you know how a system is intended to operate. Anything less than this is wild guesswork, unbecoming of a technician. Our next illustrated example problem also features unknown values. Let's apply our knowledge of basic series and basic parallel properties and solve for the desired unknowns. Here we're presented with a series parallel circuit supplied by an unknown voltage source, employing a ground reference, and some observed voltage values making use of the ground reference. A voltmeter in this position is observing a 58.5 volt difference from the top of R2 with reference to ground. And a voltmeter placed in this position is observing a 42.4 volt difference from the top of R4 to ground. Notice we're employing a ground reference to make these voltage measurements, and at no time did I move the reference lead of my voltmeter. My advice is to visualize this circuit at the nodal level and from the perspective of flowing current. Current in a single path will be the same. Voltage across paths in parallel will be the same. For every rise there is a drop, and what goes in must come out. I'll start by assigning some nodes. Node A is the junction of the top of R1 and R3 and our source. Source current should split here. Node B is the junction of the bottom of R1 and the top of R2. R1 and R2 appear to be directly in series with one another. There is no possible deviation for current leaving R1. It must enter R2. Node C is the junction of the bottom of R2, the bottom of R3, and the top of R4. All current leaving R2 and R3 must recombine and flow through R4. Our final node is our ground reference node, that which was employed to make the voltage observations. Our voltage from the top of R2 to ground is saying that node B is 58.5 volts higher than ground. Our voltage from the top of R4 is saying that node C is 42.4 volts higher than ground. Therefore, using our understanding of double subscript notation, it can be said that VBC equals VB, reference from our common terminal of ground, minus VC, reference from our common terminal ground. VBC, therefore, is equal to 16.1 volts. Source current will leave the positive terminal and enter node A. Current will split into two paths. IS equals I left plus I right. That current traveling the right branch only travels through R3. Therefore, I right equals I3. That current traveling through the left branch must travel through R1 and R2 in series to get to node C. I left equals I1, which equals I2, because R1 is in series with R2. Finally, I3 combines with I left and flows through R4. I4 is the summation of I3 and I left. I4, since there are no other deviations, is the source current. Returning back to our nodes and nodal voltages, notice R3 is between nodes A and C, as is the series combination of R1 and R2. The series combination of R1 and R2 could be replaced by an imaginary resistor I'll call R'. R' is in parallel with R3, and this parallel combination will experience the same voltage drop. Vr' equals V3. Since R' is composed of R1 and R2 in series, it stands to conjecture that V1 plus V2 equals Vr', which equals V3. Additionally, R' could be combined in parallel with R3 to make an imaginary resistor I'll call R double prime. R double prime is in series with R4 and will experience the same current through it. Is equals I4 equals IR double prime. Additionally, a KVL analysis of this simple series circuit suggests that E equals Vr double prime plus V4, where Vr double prime is the parallel combination of R3 and R', so V double prime should equal V3, which should equal Vr', which equals V1 plus V2. Now that we've got a map of the battle, how do we kick the battle off? Sift through the clues and see if you can find one toehold that can get you up to the next handhold, and from there climb to the top using basic series and basic parallel properties. One of the toeholds is right here at R2. R2 is a known resistor experiencing a known voltage drop of 16.1 volts. Ohm's law says that I2 equals V2 divided by R2. Substituting in the necessary values, we find I2 equals roughly 13.4 milliamperes. This is an approximation, and my recommendation, consistent to the advice I issued way back in the DC math lecture, is to make use of the full unrounded values via the previous results key in your calculator. If you don't follow this advice, your answers will progressively depart from mine as rounding errors accumulate. I2 is known to be 13.4 milliamperes. Since R2 is in series with R1, this implies I1 is also 13.4 milliamperes. We can use this to solve for the voltage drop across R1. Ohm's law says that V1 equals I1 times R1. Substituting in the necessary values, we find V1 equals roughly 13.4 volts. If R1 drops 13.4 volts from node A to node B, and R2 drops 16.1 volts from node B to node C, it stands to conjecture that R3 drops 13.4 plus 16.1, or 29.5 volts from node A to node C. Voltage across paths in parallel is the same. We do know voltage across R3, but we know neither the current through it, the resistance of it, nor the current entering or leaving the parallel combination of R' and R3. Or do we? The other toehold to this problem is at R4. R4 is again a known resistor experiencing a known voltage drop of 42.4 volts. Ohm's law says that I4 equals V4 divided by R4. Substituting in the necessary values, we find I4 equals roughly 28.3 milliamperes. If 28.3 milliamperes is leaving node C and traveling through R4, this means 28.3 milliamperes must have entered node C. Given we've already solved for current entering node C via the left branch to be 13.4 milliamperes, we can solve for I3 by substituting these values into our KCL analysis at node C, where I4 equals I3 plus I left, and solve for I3. Substituting in the necessary values and solving for I3, we find I3 equals roughly 14.9 milliamperes. Now we know both the voltage across and the current through the unknown resistance R3. Ohm's law states that R3 is equal to V3 divided by I3. Substituting in the necessary values, we find R3 equals roughly 1,987.7 ohms. If you're getting 1,979.9 ohms, it's because you're not listening to my advice about rounding only the final answer. Keep previous results and make use of the previous results during calculations. Finally, we're asked to solve for the source voltage E. KVL analysis of this loop or any other loop in this circuit suggests that E is a source of approximately 71.9 volts. All desired unknown quantities have been solved for using efficient and effective means. Before we close up this lecture, let me leave you with this final assessment exercise. This is meant to be a challenge, and no, I am not going to directly give you the answer. I will leave the answer in the information section accompanying this lecture. Don't peek. I'm expecting you to struggle with it. This problem won't be easy. However, it requires absolutely no additional skills besides visualizing the circuit at the nodal level and from the perspective of flowing current. Current in a single path is the same. Voltage across paths in parallel is the same. For every rise there is a drop, and what goes in must come out. Given the following components and instruments and their observed values, solve for the voltage drop across all components. Solve for the current through all components, and solve for all unknown resistances. Our source has a magnitude of 21 volts. R2 is a magnitude of 1.5 kiloohms. R3 is also a 1.5 kiloohm resistor. Ammeter X is observing 10 milliamperes when placed in this position. Voltmeter Y is observing a 4 volt differential in this position. Ammeter Z is observing 2 milliamperes of current in this position. If you are struggling with this, here's a hint. Visualize this circuit from the perspective of flowing current. Think of the path current takes on the way to R2. Think of the path current takes on the way to R3. Think of the path that current takes when traveling to R4 and R5. This simple analysis alone should set you up for success. If that's not enough, look at the circuit from a nodal level. Voltage across paths hooked in parallel is the same. Think at the nodal level. Remove the ammeters and replace them with short circuits. Ideal ammeters are 0 ohm resistors. Remove the voltmeters. Ideal voltmeters are infinite resistances. Ideally, these instruments don't affect the circuit. Assign nodes for our circuit. Voltage across paths hooked in parallel should be the same. The voltage from B to D should be the same regardless of whether you travel from B to D via R2, R3, or R4 and R5. Come up with a plan. Find a toe hold. From that toe hold, find a handhold and keep climbing. In closing, check your work. Numerous opportunities exist to do so. If you've got time, it's a recommended practice. If you observe contradictions, you're performing the analysis wrong. You're making wrong observations in the correct circuit, or you're making correct observations on the wrong circuit. In conclusion, this lecture took an introductory look at series parallel electrical relationships, circuits that combine the characteristics of both basic series and basic parallel configurations. We discussed basic properties for series parallel configurations and made use of previously discussed basic series and basic parallel properties to determine unknown circuit properties based off limited observations. Additionally, we discussed how shorts and opens affect series parallel circuits. In summary, I have used no new skills in the discussion of series parallel circuits. The first step in series parallel circuit analysis is to visualize circuits at the nodal level and from the perspective of flowing current. Current in a single path is the same. Voltage across paths in parallel is the same. For every rise there is a drop, and what goes in must come out. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.